The Foucault pendulum is credited with being one of the world's first scientific devices to prove that the Earth rotates about its own axis.
The idea behind a Foucault pendulum is that a pendulum on Earth, or any rotating planet, given it can oscillate long enough, will visibly change orientation. That is, the plane on which it swings will turn, showing that the Earth beneath it is rotating. The goal of this project is to simulate the motion of such a pendulum using the known forces which act upon a pendulum, and attempt to recreate the rotational phenomena through the simulation. Additionally, we aim to explore how changing the parameters of the system influences the motion of the pendulum, namely the rate of rotation of the pendulum. We also look to validate our simulated pendulum by comparing its motion to the experimental data collected by Foucault himself, as well as the known analytical solutions which describe the behavior of Foucault pendulum.
The experiment posits that a pendulum undergoing simple harmonic motion will not change its direction in the inertial reference frame. What this means is that, as you can see in the figure on the right-hand side, you can see that the pendulum will oscillate between points A and B back to A. This is simple harmonic motion. It will oscillate back and forth in this direction only, and you can see a front view of it in part A on the left. It won't oscillate side to side, it'll just oscillate back and forth. However, even though this pendulum will not move side to side, or will not rotate in the inertial reference frame direction, the ground beneath it will. To prove this, a pendulum should be created that is attached to a very long cable, and the pendulum itself should have a very large mass to ensure that it oscillates for long enough for the effects of Earth rotation to be seen. For the purposes of this experiment, French scientist Léon Foucault used a 27.67 kilogram weight and suspended it from a 61-meter long wire. He then attached a small stick to the end of that weight so that as it swung to its low point, where it had maximum velocity, it would draw a line in a pit of wet sand. As the pendulum was left to swing over an hour, it was found that the line being drawn rotated 11.25 degrees. This conclusively showed that the Earth rotates about its own axis. So, to explain why this rotation occurs, we consider this thought experiment. Say we take the pendulum and we take it to the North Pole, being represented over here, and we have someone like an astronaut observe it from the top. Now, once the pendulum is set in motion, to the astronaut, it's not going to seem like the pendulum itself is rotating. Instead, what they're going to see is the pendulum staying still, oscillating in its normal back and forth way, and the Earth rotating underneath. This visualization is shown in a MATLAB video that's now appearing.
Here we see the perspective from someone in space. As we can see, the pendulum is moving in one plane, and the red circle represents a point on Earth, which is rotating beneath it. So the astronaut, or whoever is in space, will just see the pendulum moving in one direction while the Earth rotates beneath it.
Now, this is because in the inertial frame of reference, in this case, which is space, the astronaut's not going to be able to see anything happening except the Earth rotating underneath. However, if we have someone standing right next to the pendulum itself, and they're accounted for over here, so they have this view because they're standing right next to the pendulum on Earth, and they are rotating with Earth in the direction indicated by these arrows. They're going to see a completely different view that you are now seeing on this video, again represented by MATLAB.
Here we see the same scenario, but from an observer on the Earth. The person on the ground moves with the rotation of the Earth, while the pendulum stays in constant plane of motion, and so for an Earth observer, it appears as though the pendulum rotates in a circle rather than them. This is shown through the red circle, which is supposed to represent a point on Earth, but since the observer on the ground is rotating with the Earth, this appears to be motionless, while the pendulum turns about.
So what they are essentially seeing is, since they are part of the actual movement of the Earth, they're going to think that, oh, it's the pendulum that's actually turning. So this movement in the non-inertial frame, in which in this case is the Earth, is accounted for by the Coriolis effect.
Now we know that the swing of the pendulum will rotate, but how quickly, and what affects the period of rotation? Known analytical solutions tell us that the period of rotation of the pendulum will be equal to the time of a sidereal day over the sine of the latitude. So we will use this simulation to we will use this equation rather to calculate how long it should take for the pendulum to make a full rotation in our simulation, and compare the simulation results to this known analytical solution. This is done so we can determine the error of our simulation. However, let's first discuss why this is true. If we look at this image, we can see the rotation vector going through the pendulum. So the rotation it applies to the Earth is all going towards moving the ground beneath the pendulum, like so. We can see that the Earth's rotation vector is just rotating the ground around the pendulum completely. However, when the pendulum is not on a pole, the Earth's rotation vector is not fully responsible for the rotation of the Earth and around the pendulum. If we split the omega vector to two components, one going through the pendulum pivot and one perpendicular to this, we see how only this one component rotates the Earth around the pendulum, causing the apparent rotation on the Earth, while the other component is responsible for rotation in this direction of the Earth, which will only move the pendulum along the Earth with it and not rotate the Earth around it. Now, since this component of the rotation vector, the effective rotational vector, and by effective I mean portion of the rotational vector which is actually rotating the Earth around it, this effective rotational vector is going to be smaller than the full rotational vector because it's only a component of it. So the speed at which the Earth rotates around the pendulum is slower than it would be at the pole because this rotational vector is smaller than the original. And since the Earth rotates around the pendulum more slowly, the time taken for this apparent rotation of the pendulum to turn around itself will be longer, hence why the period of a pendulum which is not on a pole is longer than when it is on the pole.
Now let's model the actual forces and going on in that pendulum system. So there's four forces governing our system. That's the force of gravity, the tension force, the Coriolis effect force, and the force of centripetal acceleration. So let's start with that force of gravity. It's the simplest. Force of gravity is just mg. Now for the tension force, this is where things get fun. The acceleration of a centripetal is v squared over r. Multiplied by m, you get mv squared over r. We also know that with the pendulum, you will have tension going towards the center of the pivot, and you also know that due to the force of gravity in the downwards direction, you will have something going in the opposite direction of the tension, which is mg cos theta if you assume this to be your theta. To t minus mg cos theta, the net has to be mv squared over r. So we can reorganize this to solve for the tension force, which is mg cos theta plus mv squared over r. Moving on, let's talk about the Coriolis effect. Now the Coriolis force, now that is modeled by 2 times omega cross v. Now omega, over here, omega is the rate of rotation of the Earth in radians per second, and v represents the velocity as a vector of the actual pendulum as it is moving. Finally comes the centripetal force. Centripetal force is found by omega cross r. R represents the position vector of the pendulum relative to the center of the Earth. However, in our calculations in the end, we are going to assume that the centripetal force is negligible or it's nothing. Omega already itself is pretty small. Now, if you're just squaring that like you are over here, it's going to make it even smaller, which means it's pretty much insignificant, which is why we can just factor it out completely. Another thing we're assuming that air resistance is negligible in our system. So it's pretty much ignored, and so what we're thinking is we're assuming that the system is in a vacuum or in an area with very low air density. That's it.
To simulate the motion of the pendulum, we will determine the forces acting on the pendulum bob and use numerical integration in order to compute the changing velocity and position of the pendulum across very small time steps, effectively simulating the behavior of the pendulum mass. The simulation is written as a MATLAB script and can be found in the supplementary files. In order to perform this simulation, we must first set up the coordinate system. First, we define the z-axis as the axis pointing away from the surface of the Earth, and the x and y axis will be such that the xy plane describes the Earth's surface, as shown in here. Additionally, the origin of the coordinate system is the pivot of the pendulum. The general methodology behind the simulation is to set up a pendulum at some initial point. Then, for the given position of the pendulum mass, we calculate all the forces acting on the bob, which is used to determine its acceleration vector. The acceleration is written as the differentiation of velocity, which, through numerical integration, can be calculated for that time step, and the velocity of the mass can be updated. This process is equivalently repeated using the velocity to determine the new position of the mass for the next time step. We continue updating the position of the mass until the line formed by the pendulum swing has made a full rotation, or a rotation of some given amount, before stopping the simulation and printing the time taken for this rotation to take place. To start the script, we first define physical characteristics of the pendulum and initialize the system. This includes setting the length of the pendulum, the mass of the bob, the initial angle the pendulum makes with the vertical or z-axis, theta, and all physical information of the system. Additionally, we calculate the initial position vector using the length of the pendulum and the initial angle, theta. The velocity is initialized to the zero vector since we assume that the pendulum begins from rest at one of its peak heights. Before determining forces, we must also define the omega vector, which is the rotational vector of the Earth. That is, this is the vector which points along the axis of rotation of the Earth with a magnitude equal to the Earth's rotation in radians per second. Because we have defined our coordinate system to be convenient for a pendulum of the Earth, the omega vector will change with respect to latitude. This is because we must translate the Earth's omega vector onto the coordinate system of the pendulum, which will be in different places on the Earth depending on the latitude. We will determine what the rotational vector will be in our defined coordinate system in the following video. So in this graphic, we can see our Earth with our pendulum and our omega vector, and we can see we have the x and z axis and the y-axis that we've defined as part of our coordinate system for the pendulum, although the x and z is really important because we want to put our omega vector onto our coordinate system, project it onto the coordinate system we've defined. So what we're going to do is extend in the x direction a line, which we'll notice that the angle between omega and this line in the x direction is the same as the latitude with theta, the angle of the latitude. So if we project omega onto this line, it's going to have a magnitude of omega cos theta, and that's going to be on the same line as our x-axis. And then if we project it in the other way, in the z-axis, our component of omega will be omega sine theta. And note here that omega sine theta is in the same direction as the z-axis, so our z component is going to be simply omega sine theta, and the x-axis, they're pointing in opposite directions. So the x component of omega is going to be negative omega cos theta. And that's how we convert our omega vector onto our coordinate system. But what exactly is the magnitude that we're going to be using in our simulation? Well, as we discussed before, the Earth spins around itself in one sidereal day, which is 23 hours, 56 minutes, and 4 seconds. So the magnitude of omega is simply going to be, as shown here, 2 pi radians, and that will be over our 23 hours, 56 minutes, and 4 seconds. Although when we do the calculation, we're going to convert this time into seconds and do the 2 pi over that equivalent seconds. Now, this is actually 2 pi radians over 86,164 seconds, which is approximately 72.92 microradians per second. Next, we calculate all the forces acting upon the mass. Gravity is simplest since it is constant no matter what the position of the mass is, which is simply negative mass times the gravitational constant for Earth. Tension is determined by first calculating the magnitude of the force, which, as shown before, is mg cos theta plus mv squared over r. Then, a unit vector is created from the point of the pendulum to the pivot, or the origin, which is multiplied by the magnitude previously calculated. Finally, the Coriolis force is calculated through the known equation negative 2 times m times omega cross velocity. Note that because the velocity of the mass is mostly on the plane of the swing, and the Coriolis force is omega cross the velocity, this force will act perpendicular to the plane on which the pendulum swings, which will push the mass to the side. Because of this, the Coriolis force is actually was responsible for the pendulum's rotation. Once all the forces are calculated and summed into a net force vector, we divide it by the mass of the bob to get the acceleration for that time step, and calculate the velocity at the next time step by equating it to the velocity at this time step plus the acceleration we just calculated multiplied by our change in time, or our time step. Through this numerical differentiation equation, and more specifically the forward finite difference method, we calculate the velocity of the pendulum bob at the next time step, and similarly use the same method with the velocity to calculate the next position of the bob itself. We continuously calculate the velocity and position of the mass at the next time step over and over and over again. We repeat this process until the line along the pendulum swing has rotated a given amount. This rotation is referred to as the precession of the pendulum. To do this, we check at every iteration if the velocity in the z direction goes from being 0 or positive to being negative. If this is the case, we know the mass has reached an apex at the far end of the pendulum swing. Every second time this occurs, we calculate the angle that the bob's position makes with the x-axis using the x and y position. We will call this angle phi. Now, we only consider the angle at every second time we reach an apex in the swing, so that we can record phi only at the pendulum's forward swings to get an accurate measure of the change in precession. Every time we calculate a value of phi, we compare the value with the last calculated value of phi to determine the change in the angle since the last recording. This is added into a separate angle variable, which we will refer to as true phi. The reason for this is so that we may record the angle at which the pendulum has rotated since the simulation began, rather than simply measuring the angle it's at now. This allows us to tell if the mass swing has rotated 2 pi radians, 4 pi radians, or more, rather than just being limited to the negative pi to pi range. Once the true phi passes our stopping condition angle, we stop the iterations and print the time taken for the precession of the pendulum to take place.
Since all simulations are only approximations of systems, there are sources of error that have to be analyzed and accounted for. Here we can expect that since we're using explicit time integration in calculating the velocity and position of the mass, there will be an error associated with time steps and approximation. This error arises from the fact that we're not using an infinitely small time step. This graph is a figure of acceleration over the bob over time.
Notice how the acceleration plot looks sinusoidal, but in fact it's not quite. If you look at the circles on the graph, these are marking the points of inflection in the acceleration plot. Notice how they're below the vertical offset. This will be significant later.
To find the position, we're effectively sampling the sinusoidal-looking signal at certain points and rectangularly approximating them to get a velocity value. There are clearly 2 regions visible in the signal. The first one is where the tangent of the curve is continuously falling, which is denoted by the orange circles. The second one is where the tangent to the curve is continuously rising.
At regions where the tangent slope decreases, as seen in the left image, the area calculated by the rectangular approximation is greater than the actual area under the curve. This is because the access area calculated, shown by the blue number 1, is greater than the area under the curve which the approximation fails to calculate, shown by the black number 1. The net error, therefore, is positive, and we overestimate the area under the curve. Conversely, when the tangent slope increases, as seen in the right image, the area overestimated by approximation is smaller than the underestimated area, so these regions will result in a net error, which is negative. Because the point of inflections are not in the middle and are rather lower than the middle of our sinusoidal-like shape, then what ends up happening is we have more regions where the tangent slope is decreasing rather than where the tangent slope is increasing. As a result, we have more regions where we're overestimating the area rather than underestimating the area, causing a total net overestimation of the area. Since this is the acceleration, when we calculate the area underneath, what we're calculating is velocity. So we're overestimating the velocity, and as a result, we're overestimating the rate of rotation of our pendulum. So we're actually calculating a period of rotation of our pendulum, which is faster than what we would expect in real life.
The original experiment of the Foucault pendulum was conducted at the Pantheon in Paris. His pendulum made a full circle in approximately 31.8 hours. This can be verified with the same formula, where the pendulum subtends an angle of 360 times sine phi in 24 hours. Phi equals 48.8462 degrees at the Pantheon, and this gives us an angle subtended of around 271 degrees in 24 hours. Thus, a full 360 degrees will be completed by the pendulum in around 31.8 hours. The value obtained from our simulation is only around 1% off at 31.45 hours.
Notice also from the data we've collected by experimenting with Foucault's original setup that choosing an appropriate time step is critical to the accuracy of the simulation. As predicted from our error analysis, we make the observation that all our simulation's results calculate a quicker period of rotation when compared to the known analytical solution. However, the magnitude of the error varies greatly with changing time step. Using a delta t of 0.0005 seconds, we see only a 1% error. However, with only double that time step, at 0.001 seconds, we see the error increase fivefold to 5.135% error. Then, with a delta t of 0.01 seconds, we see a massive error of more than 30%. So while we validated the accuracy of our numerical solver, when we try running the simulation at several different altitudes to see how the period of rotation differs, we will use a time step of 0.0005 seconds to ensure that the error is kept to a minimal.
We're now going to estimate the value of the rotation period at different locations across the Earth. We have locations at London, Toronto, and Beijing with latitudes in the decreasing order. So London has a latitude of 51.5 degrees, Toronto has a latitude of 43.6 degrees, and Beijing has a latitude of 39.9 degrees. We can see that the value from the simulation goes down as the latitude increases. And we can also see that the error percentages of our simulation are all very close to zero.
This indicates that our solver is very accurate across a wide variety of latitudes. It also shows that our solver is behaving as expected when we compare it to the analytical solution, because as our latitude increases, the time it takes for a full rotation to occur decreases. And because our analytical solution said that the period at which the pendulum will rotate is equal to a sidereal day over sine of the latitude, we should expect as we approach a value of sine of 90, being at the North Pole, the period will approach a sidereal day. And as the latitude decreases, we will get values in the denominator for that equation, which are less than 1, increasing the total period for how long it takes the pendulum to rotate, which is exactly what we're observing in this data. The experiment Foucault performed was huge at the time because of its value to the scientific community. People at the time already knew the Earth rotated. This was nothing new. However, Foucault's original experiment was very valuable in other ways. Firstly, the system is relatively simple and can be recreated fairly easily. Additionally, it provides a way for someone to easily visualize the rotation of the Earth. Anyone can look at a Foucault pendulum swing and can notice that it has changed orientation. No scientific knowledge or experimental experience is required to see the effect of the Earth's rotation. In this respect, the pendulum has great scientific educational value. Even more valuable is that the experiment was the first to not only show that the Earth rotates, but also measure the rate at which it rotates. The pendulum doesn't just have purely scientific value either. It has very important applications in engineering. An object in oscillatory motion being used to measure the rate of rotation of its reference frame through analysis of the Coriolis effect is the basis for the instrument which marks the biggest leap in technological advancement since fire. The MEMS gyroscope. That's right, as we all know from MTE 202, MEMS gyroscopes force a mass to vibrate in one plane and allow the rotation of the device to force the mass to move in another plane. And the mass's position is measured on this axis in order to determine the rotation. While the Coriolis force was known for years before Foucault performed his experiment, he created a system which had more or less constant motion, which could take advantage of the force in order to measure the rate of rotation of a body, and thus his pendulum is in effect a gyroscope. Gyroscopes today are critical instruments in many devices used by everyday people, as well as advanced scientific and engineering machines. They have applications in everything from your smartphone to spacecrafts to making awesome games for MTE 241. Specifically, gyroscopes are often used in stabilization technology, for example in camera stabilizers, which use them to determine the orientation of the camera and correct for imbalances and rotations. They're also used in robotics to allow a robot to know the orientation of its limbs, feedback which may be necessary for precise and quick movement of an end effector. Using a gyroscope for robotics arms is also a huge advancement to engineering students because they don't need to solve inverse kinematics equations and can cut their numerical methods homework in half. In short, anything which may need to measure its orientation can benefit or may even require a gyroscope to function. Gyroscopes have applications in rocket control systems, virtual reality, even physical therapy. This image here shows a glove which uses gyroscopes to help stabilize the hands of those with Parkinson's. All these systems and much more all benefit from the principle of gyroscopes and the measurement of the rotation of an object, all of which extends from this simple device, the Foucault pendulum.